Okay, so let's discuss a question from machine design. You have a journal bearing which has a shaft dia. So you have a shaft dia, okay, and you have a journal bearing. So I am just magnifying the clearance here just for the sake of understanding. So this is journal bearing and this is my shaft. So assuming that clearance is uniform because nothing has been mentioned, okay, and you don't have the hydrodynamic effect, it's just the shaft is rotating and you have a bearing, okay, the clearance is uniform. Okay, the dia is given 50 mm, the length is given as 100 mm of the shaft rotates at 200 rpm, and viscosity, dynamic viscosity is given as Pascal second. The clearance is 0.020 mm and the loss of power is asked. Okay, so when the shaft is rotating like this, okay, when the shaft is rotating like this, the fluid will exert a shear stress, a frictional shear stress, which is in this direction, tau. And this tau will act uniform over the entire circumference and over the entire length of the shaft. So on the surface there will be a tau, so tau into the cross section area, which is the cross section length, which is 2 pi r, into the total length. So this is the total peripheral length throughout the circumference and throughout the length, so 2 pi r into L. So this is the total force which is at a radius r from the center. So this total force into r will be the effective torque coming at the center, effective frictional torque, and which your shaft has to oppose. So this torque is the frictional torque, and therefore the frictional loss in power basically will be this torque into speed. Okay, so it is tau into 2 pi r square into L into omega. So this is your formula for the frictional torque. Now we can calculate everything, but how do you calculate tau? Now tau, assuming if the gap is very small, you can just assume that the fluid behave as a Newtonian fluid, and the shear stress is related to the velocity gradient by mu dv by dy. This is like between two plates. Now you are applying at the between the shaft and the bearing. So mu dv by dy, so it's the thin gap, and assuming that it's a linear variation of the velocity of the fluid in that clearance. So this is v, this is 0, and this is your clearance. So it's mu v by c, and v is again the surface speed of the shaft, which is r omega by c. So substituting everything in this, which we get mu r omega by c into 2 pi r square L omega. So this is 2 pi L omega mu by c, 2 pi L omega mu by c into r cube. So 2 pi mu, and you have omega square here, sorry, mu, so L omega square mu by r c. Okay, so now let's substitute 2 pi, okay, omega, well, speed is 200 rpm, so omega will be 2 pi n by 60, which will be 2 pi 200 by 60. Okay, so that is nothing but 20.94 rps, radians per second. So 20.94 whole square, mu is given as 20 millipascal seconds, so that is 0.02. Let's look at, yeah, it's 20 milli, so 20 into 10 power minus 3, and radius is given as the 25, I mean dia is 50, so it is 25, so 0.025, and the clearance is given as your 20 mm. So let me write 0.020 into 10 power. Everything we are computing in meters. So this is your complete thing, the loss of power, and this comes about 4.3 watts. So 4.3 watt of power goes in resisting the friction. So this is a very good problem because it involves everything. Don't confuse this with the clearance is not given and need to assume something. Just think about the problem, what is the best you can do. And this is in fact a derivation which is done actually. So 2 pi L, we have done this derivation in fact. So 2 pi L, L is something which I have not included. L is basically 100, so it will be 0.1. So 2 pi L, and then the speed whole square, and the mu and the radius. Yeah, so this is what, so r cube actually. So I have okay, substitution you can just substitute, but check that whether you are getting this formula. So 2 pi L omega square mu into r cube by c. So thank you. 4.3 watts is the power, and I mean the options are all confusing, so D is the answer. Thank you.